So today I'm just going to review for the exam. You can take the exam on Moodle anytime this week. You have 75 minutes to take it once you start it up, and there's 15 questions, so you have 5 minutes per question. And it's just multiple choice. If you see anything that looks strange, send me an email. It's not uncommon to have bugs in the question. Usually what I do is, if someone finds a bug, I usually just give everyone credit for that question that had already taken it, and then I fix it for anyone that hasn't taken it yet. So, but I did redo all the questions this year as compared to last year, so there's a chance there might be an issue, but let me know if you find something strange. It's going to cover everything we've covered so far in the semester, so basically RISC, system Verilog, and microarchitecture. And then possibly some basic logic circuits, conceptual questions. Yes?
What's Moodle? What is that?
Sorry, Dropbox.
Oh, Dropbox.
Yeah, Dropbox, dropbox.csce.sc.edu.
So it'll be just like how the quizzes were then?
Right,
Okay.
yeah, it's set up just like the quizzes, except you can only take it once.
Yeah.
Yeah, Moodle is the software, Dropbox is the URL. Okay, so I haven't gone over quiz 3 yet. I think this was due last Monday after class, so I didn't talk about it. This one is covering microarchitecture. So you want to make sure you're comfortable with these concepts. And I have some more practice questions I'll show you here after I get through the quiz. So this question says, consider the RISC-V microarchitecture shown below. What are the values of regwrite WB, ALU source EX, and regcell WB? And notice I'm using Verilog syntax here, where I'm taking these three values and I'm concatenating them together with these little curly brace things. So what I'm asking is that you figure out what these values are and then concatenate them into one value. So we're looking at the situation where we have a multiply H being fetched, a load up immediate being decoded and executed, and an XOR I being written back. So regwrite WB, regselect EX. I'm not sure why I have. Okay, I don't know why I have regselect WB circled, but I asked for regselect EX. Okay. Whoop. That's glitched, huh? Huh. Okay. That's strange. Hold on a second. Lectures. Okay, yeah, all right, so I'm showing the two pictures that I presented in class. These are meant to represent the same design. I'm just showing them as two different figures so they're easier to read. So regwrite WB, what does that mean? That just means that if the instruction in the write back stage is writing to a register, then that should be set to 1. In this case, the instruction that happens to be in write back is XOR I, which does write to a register. In fact, just about all the instructions that we've talked about write to a register. So regwrite WB should be 1. If I had asked you for regwrite EX, then that would be the same thing, except it would correspond to the instruction in the EX stage, right? So that would be the LUI instruction, which also writes to a register, so that would also be 1, right? So regwrite EX and regwrite WB are both 1 because both the instructions in those two stages write to a register. Then ALU source EX is corresponding to the instruction that's in the EX stage, which is LUI. And ALU source, now that name is arbitrary, by the way. I just made that name, well, I didn't make it up. It came out of the Hennessy and Patterson book, but it's an arbitrary name. In order to figure out what it does, you have to look at what it's doing in the design here. So yeah, ALU source EX, I have it circled here. That's the correct one. And that signal is the select for a MUX that controls the second input on the ALU. Now it's a little bit vague because I don't actually show what that second input is, but it's implied. It's an ALU. It does, scalar operations on two inputs. So that's the B input, right? The second input. And ALU source, the name also suggests that it controls the, source of the ALU, the operand source. So the option there is register or immediate, sign extended immediate. So the question is, it's EX stage, LUI is the instruction that's in the EX stage. So what input into the ALU does LUI use? Well, it doesn't use either one, actually, right? Because the LUI is just taking the immediate and sticking it in a register. There's no ALU operation associated with that instruction. The ALU is a don't care. And the reason for that is because the ALU's output is going to get blocked by that MUX. So the ALU's output isn't going to go anywhere. So the ALU is going to do something, but whatever it does is it just produces a don't care. So the answer for that is don't care. If I had asked you for ALU source WB, well, I wouldn't have asked you that because there is no ALU source WB because the ALU doesn't do anything in the write back stage. It's only an execute stage thing, right? Reg select WB is associated with the XORI instruction, and it is here. It's controlling the MUX that controls what goes back to the register file, what gets written back. Now again, I understand it's a little vague because the input port that I'm connected to there is not labeled, but as I mentioned, generally when you have a block diagram, the data flows from right to left, right? So the idea is that that's going to be an input. Obviously, it's indicated by the arrow there, and because it's coming out of that MUX, you can assume that it's a 32-bit signal coming out of that MUX because at least the ALU output is 32 bits. So what would be a 32-bit input into the register file? That'd be the value we're writing into the register. And so what value are we writing into the register for XORI? Well, XORI is an ALU op, so it would be ALU output, right? So what should I select there? 2, right? ALU. Now it passes through a register to be the output of the ALU is registered or clocked, right? Meaning that the value that I'm going to put into the register file is whatever the ALU produced in the previous cycle, which was when the XORI was in decode, right? Does that make sense? You guys with me on that? Okay. Okay, then another question. This is very similar. I just changed the instructions, did I? Yeah, I changed the instructions here that are in the stages. Reg write WB would be 1 because LUI is in WB and it writes a register. ALU source EX is corresponding to the mol H, which would be 2, right? No, sorry, ALU source, not reg select. ALU source is corresponding to the mol H. So ALU source is this guy again. So mol H, it's not an immediate instruction, it's a register instruction, so we should be using the register, right? Input, so 0, right? ALU source should be 0. And then reg select WB is corresponding to the WB instruction here, which is LUI. And so with an LUI, this is kind of the weird case where we're going to take the the immediate value, right? Instruction EX31 down to 12 and then padded with zeros. That's the upper 20 bits of the instruction, which is that weird U type. It's the immediate value. It's a 20-bit immediate. We're going to take it, we're going to pad it out with zeros, and then we have to route it through the second, in this case, the second input on that mux. So for LUI, reg select WB should be a 1. So we can route the immediate through the mux. So this is essentially how CPUs work. They just establishes these data paths depending on the instruction. So for this instruction, we just have to route the immediate into the register file. The tricky part here, though, is that you have to make sure it's being done in the right cycle, right? In this case, it's reg. Well, I was asking for reg select WB, and you know the LUI is in that stage. Does that make sense? So in order to solve this, you have to have an idea of what the instructions are doing. This is the reason why you have to be familiar with RISC-V, although generally I pick instructions that are the same as they are in MIPS, right? So you have to understand these mnemonics, what these mnemonics represent, right? LUI is load up or immediate, and these are fairly common abbreviations. They're not standard across different processors necessarily, but in MIPS and RISC-V and ARM, they're similar. So load up or immediate, and then mul H is multiply high. We know that that's from lab. We use that in lab 1. I actually use mul HU. And add I is add immediate. I try to choose instructions that are common instructions, right? Okay. Okay, this is another one. It says question 1 at the top, but this was question 3. So this one was reg write, ALU source, EX, and reg cell WB. Same thing. Yeah, all three are the same control signals. So reg write WB is corresponding to the CSSRW instruction. Okay, now this one is a little weird because CSSRW, does that write to a register? It does, right? It's supposed to. Now in our CPU, it may not. If you're using CSSRW to read the switches, right, then you can have it not write a register. But the actual RISC instruction, if you look at the definition of what the RISC instruction does, is it's supposed to always be writing to a register, even if that register is 0. And of course, in which case it just throws away the value it wrote. Okay? So CSSRW would have a 1 for reg write WB. ALU source EX is matching up to the add I. In this case, the ALU source would be it would be routing in the immediate because it's an add I. So the ALU source would have to be a 1. And then reg cell WB refers again back to the CSSRW. And now in this case, what are we writing into the register file for CSSRW? The GPIO, right, or the input. It's an input. It takes an input from outside the CPU or a control register somewhere within the system on chip. So in that case, we want to use 0. Reg select should be 0 because that should be bringing in an I/O register for CSRRW. Make sense? Okay. Okay. How many cycles is required to perform a write to a synchronous RAM? 1. But even if I had said asynchronous RAM, it would have been the same answer, right? It always takes 1 cycle to write. The difference between synchronous and asynchronous RAM is how many cycles it takes to read, right? What is the result from performing a RISC-V mul H instruction on input values 1111 and 0001, assuming the registers are 4 bits wide. So this is going to be assuming that these are signed, right? Because there's a mul H and a mul HU. So as a signed number, a 4-bit value would have a range of -8 to +7, right, in 2's complement. And so if the number were 1111, that would represent a -1, right? If you remember from 211, 212. So we're multiplying -1 times 1, and the answer is -1. And the mul H gives you the upper 4 bits. So if you had a -1, the upper 4 bits as an 8-bit product would be all 1s. Right? This was a bad example, though. Oh no, it wasn't, because if it were mul HU, then we would not be multiplying -1 by 1. We'd be multiplying 15 by 1, in which case the answer would be 111115. But that would be the lower 4 bits, right? And the upper 4 bits would be all 0s, right? So, so the mul multiply will always give you the same lower bits, regardless if it's signed or unsigned. But the upper bits will depend on whether it's signed or unsigned. Okay. All right, so that was the quiz. All right, so now I got a bunch of example questions I wanted to run through here. Wow, you're not going to let me zoom? Okay, hold on. Let me close Office. Okay, now we're good. Okay, here we go. Okay, identify any problems which could be compiler errors or improper design practice with the module below. So module foo, we have 2 3-bit inputs A and B and 1 4-bit output C. And the module just has a single always com statement in it, which it's inside that always com, it's just an if then else. And we don't need a begin and end because the if then else counts as one statement. So we don't have to, you can put a begin and end, but you don't need to in this case because there's only one statement in there. And so it says if B, then assign C equals A and B, else assign C equals A or B. So in this case, the problem is the assign. You can't do an assign in an always. You would take the assign out and just assign. You would just say C equals A and B. Why? Arbitrary syntax rules.
So you just do it before that?
You could, well, if you could take the assign out of the always statement, but then you would have to use a trinary operator, right, the question mark thing. So you often will have a choice between an assign or an always, right? In this case, whoever wrote that tried to do both at the same time. Okay? I think that's the only problem with that. Is that the only problem? Oh, the other issue is, there's another issue actually here too. C is 4 bits, and A and B are only 3 bits, and so we would only be assigning 3 bits on C, right? And I don't know how that would be reconciled. Probably the most significant bit of C would be an X, I would assume, right? You don't want to do that. That's not a good idea. And any other issues?
Can you explain that problem again?
Yeah, so the bitwise operator, the and, right? It's like taking, like, let's say A was 0, 0, 1, and B was 1, 1, 1, right? They're both 3 bits because they're 2 down to 0, right? If you say A and then ampersand B, that's going to do a bitwise and for each individual corresponding bit, right? So you're going to get you're going to start with, well, you don't have to, like, we'll start with the least significant bit. So that would be 1 and 1 is 1, and then 0 and 1 is 0, 0 and 1 is 0, right? So that's going to produce a 3-bit result because both of the input operands are 3 bits. Yeah, it was declared as 4 bits, yeah, because of 3 down to 0. So I don't know what would happen if you're assigning 3 bits to 4 bits. I'm not even sure what would it do. Yes?
What does the conditional just having B mean? Like, does that mean that B has to be 1, 1, 1?
I believe anything that's non-zero in B will be true.
I see.
But you're right. I think that's valid. It's a little uncommon to write it that way, though, but because since B is not binary.
Okay, yeah.
But I believe it uses the same rules as C. In order for it to be false, it would have to be all zeros. Okay, next question is, to what value will the following system Verilog code set to signal B when A is 1011? So this is a module called bit manipulator. It has a 4-bit input A, a 4-bit output B, and it assigns B using bit twiddling, bit swizzling, bit manipulation. I don't know what they call it, whatever. Basically, it just rearranges the bits a little bit. So A bit 0 is 1 because bit 0 is the rightmost bit. So the first bit of B, sorry, let me scroll back up here. The first bit of B would be the last bit, of A, which is 1. Then we have the second to rightmost bit of A, which was also 1. And then followed by 2 copies of bit 2, which is, that's 0, that's 1, and that's 2. So the bit 2 is 0, and we need 2 copies of that, so 0, 0. So it would assign, B would be assigned to 1, 1, 0, 0. Okay? So we've got concatenation, slicing, and duplication going on here in one statement. Slicing is when you take, bits out of a signal with the bracket. Concatenation is the curly brace with the commas, and duplication is the double curly brace with the number of duplications. I think that's pretty much all of the bit manipulation operators in Verilog. Write a system Verilog module named parity. It receives 3 1-bit inputs A, B, and C. It produces a 1-bit output Y that is true if an odd number of inputs are true. So module parity, input A, B, C, output Y. Now, this will work, but I like to put the logic in there as well. And the reason for that is, with the input it doesn't matter. You don't have to say input logic. You could just say input A, B, and C. But with the output it does matter, because if you don't put the logic for the output, then you can't set it with an always statement. Now, why? I have no idea. Right. I don't know. Like, so if I were to do this, if I have inside the module, if I say always y equals, that would fail. I should say always comb rather, sorry. Always comb, there. Always comb y equals 1, that'll fail. It'll say you cannot assign a behavioral value to a structural net expression. Don't know why. On the other hand, though, if you did this, assign y equals 1, that'd be fine. However, if you put the logic in there, output logic y, then you can use either an assign or an always to set that, or another structural expression, like you can have it driven by a module. Does that make sense? So it doesn't make sense, but that's just a rule. So as a result, I just always put logic. I always put input logic, output logic, It's a little extra typing, but it avoids this issue. Okay, so yeah, so how do we solve this? The easiest way, I think, would just be say A XOR B XOR C, right? I think that's the easiest way to do it. There's other ways to do it. You could say, you could actually do, you could do this, A, B, C, like that. You can use a reduction, an XOR reduction operator. So in this case, I'm creating a 3-bit signal by concatenating A, B, and C, and then that's going to reduce it by basically creating a 3-input XOR gate. So that would work. I could also do always underscore comb and say if A plus B plus C is equals to 2D1 or A plus B plus C equals 2D3, then Y equals 1. That would work too, I think.
How would this show if the exam were taking since it's multiple choice?
Yeah, it's multiple choice, so you wouldn't have to type it. You just have to pick one of the options that I wrote. That's correct. I think that makes sense, right? If you add all three, if the answer is 1 or 3, then there's an odd number of bits, right? Okay, next question. Consider the design of the 3-stage pipeline CPU design shown below. Now this is the same thing I showed for quiz 3, except now I've combined everything into one design. One thing that's missing from here is, and I have to update the slide. I fixed them in the slides. I still have to upload them to Dropbox. But the ALU is missing the ALU op, which isn't relevant to these questions, so it doesn't really matter. But when you design your CPU in lab, there's an input on the ALU called ALU op. It tells the ALU what to do. And there's also an additional output called 0, which is a flag, single-bit flag. That's not shown on here. This is a, this is a simplified design that just shows the 2 inputs and the output. Okay? You guys with me? I should have shown them, but I think I was trying to simplify this as much as I could. Okay, so write a system Verilog snippet to implement the sign extend block. So you guys actually have to do this in lab, so you can actually use this code. It would just be a sign. You have to, now the problem is I'm not showing a name here. The sign extend does not have a name coming out of there. So you can call it whatever you want. I'll just call it SE equals. And so what are we sign extending here? Well, we're sign extending bits 31 down to 20 of the instruction EX. And the way I showed that is with this, I have the instruction EX and then I kind of blow it out here. And so I just need instruction EX, instruction underscore EX, 31 down to 20. And then the question is, how am I going to sign extend this? Well, the sign bits are to the left, right? So I need to basically fill in, I've got 12 bits, I need 20. So I'm just going to say 20 replications of instruction underscore EX 31. Like that. Hopefully I got this right. So there's one set of curly braces surrounding the whole thing that performs a concatenation. And then the first thing I'm concatenating has another set of curly braces that's being used for the bit replication thing. And then 20 is the number of bits that I'm replicating. And what bit am I replicating? The sign bit, which is the leftmost bit of the immediate field, which is 31 down to 20. So 31 would be the sign bit of 31 down to 20. And so then you have to use another set of curly braces because the duplication operator requires 2 nested set, right? Which is why Yeah, so there's outer curly braces for the concatenation. These two curly braces are part of the bit replication thing. The 20 is the number of bits I'm replicating. The bit I'm replicating is the sign bit of the immediate field. These two curly braces end the bit replication, and then comma instruction EX31 down to 20 is just the original 12 bits of the immediate field, and then there's one curly brace at the end that ends the concatenation. So now if you have a decoder, if you implement an instruction decoder in your CPU, then you wouldn't have to call it instruction EX31. You could just call it immediate 12 bit 11, right? Because you could have renamed this, right? My former TA for this class, Charles, was a stickler with code readability and good programming habits and practice, and he would, vomit if he saw this, because he'd say, that's way too complicated to read that. It's hard to understand that. It would be better if you outlined part of this. Take the instruction EX31, make that a separate signal name, declare it, set it. Now we're adding lines of code to do all this stuff. I tend to be a little bit more quick and dirty when it comes to this stuff. So what I've done here is I've inlined all this into one line of code. This sign extend, I've made it one line of code, but the result of this is almost impossible to understand and read what's going on there. Okay. So if I were to do it the way Charles would do it, right, you would have like logic 11 down to 0, immediate 12, and then you'd have an assign, immediate 12, stop auto-capitalizing. There we go. Assign immediate 12 equals instruction EX 31 down to 20. And then, let's see, for the sign extend thing, what would he have done? He would have done he probably would have had another signal called logic 19 down to 0 sign bits, something like that. And then he would have sign bits to be, the 20, sorry, I don't need that one. Yeah, 20 of immediate 12, 11. Actually, he also would have had some kind of constant to define the bit fields probably too. He would have went crazy with this, but yeah, you get the idea, right? Like he would have said, no, Charles would have said, you can't put 11, that's a magic number. You can't put magic numbers. You can't put magic numbers in your code, because then what happens if you want to change it, He would have defined this as a constant somewhere with a tick define. What's that?
With the name bit 11?
Yeah.
Name it.
No, he would have named it 11, and then 11, I don't know. Yeah, he goes crazy with that readability stuff. But yeah, that's you could make this complicated. My solution is one line of code. Okay, write a system Verilog snippet to implement the block that produces the GPIO signal. GPIO out signal. Feel free to use your own signal names when referring to signals that are not explicitly shown. Okay, GPIO out. What produces that? A register, right? So for a register, you're just going to say always _FF at pos edge clock, and I'm assuming the clock is called clock. Notice I don't have the clock in here. That's pretty common. Anytime you look at a block diagram, you're not going to see a clock or a reset, even though they're ubiquitous. They're connected to virtually everything, but they usually don't show it. Like if you look at the Hennessy and Patterson textbook, they never show the clock and the reset, even though they're there. In this case, I don't know what the clock's called. I'm just going to assume it's CLK. And likewise, I don't know what the input. I don't know what the output. Wait, GPIO out? Oh wait, I'm sorry, I'm looking at the wrong thing. Oh yeah, GPIO out. I don't know what that input is called there. That's read data 1, so I'll just assume it's called read data 1. So GPIO out equals read data read data 1 _ EX, right? Okay, so I've made some assumptions. I assume that the data coming out of read data 1 output on the register file is called read data 1EX, so that's an assumption. I'm assuming the clock is called CLK, and the GPIO, I know what that is because that's shown in the block diagram. So this is all you'd need then to create that little block, just a register, an edge-sensitive register. Okay, C, in the following table, mark the stage holding each of the instructions listed in the first 4 rows. Ah, yes. Okay, this one is kind of wild. Okay, so now, in this case, we want to figure out, we have 4 instructions that are going to be executed. We need to figure out, we need to map out what is happening in each of the 3 stages for these 4 instructions across 4 cycles, right? So we're assuming that in cycle 0, we're fetching the first instruction. The other instructions, which are below them on the table, but are coming in the future, right? They're later instructions in the program code, in the fetch order. They don't exist, they haven't come in yet, right? In cycle 1, we're going to fetch the second instruction. In cycle 2, we're going to fetch the third instruction. And in cycle 3, we're going to fetch the fourth instruction, which means that in cycle 1, the first instruction shown, LUI, that one's going to be executing, and it's going to be writing back in cycle 2. And the ORI is going to be executing in cycle 2. Now the LUI is going to be retired by cycle 3. But in cycle 3, the ORI is going to be writing back while the multiply is executing, while the move from high is fetching. Oh, and by the way, we don't have a move from high instruction. That's from MIPS. I didn't update this yet this is one of the examples I haven't updated for RISC-V. It's not a big deal though. So move from high is, in RISC-V, we have a multiply high instruction that just takes the upper bits of the product and puts in a register, whereas in MIPS, whenever you did a multiply, it would record all 64 bits of the result in the high and low registers, and then you subsequently had to move or copy the high and low register to a general purpose register. That's what that was. Okay, anyway, and then finally cycle 4, we're going to be writing back the multiply and executing the move from high. Okay, makes sense? Everyone clear on this part? So this is just what's going on in the CPU in each cycle in terms of what instruction is where. I don't know what's being executed and written back in cycle 0, because in order to know that, I have to know what came before the LUI instruction. Okay, so reg write EX, I don't know what's in EX, so I don't know. Is that it? Yeah. Cycle 1, reg write EX is going to correspond to whoever's in execute. Who's in execute? That's the LUI. Does the LUI write to the register file? Yes, so that should be a 1. Right? Reg write WB, well, I don't know who's in WB, so I can't answer that. Enable high low EX. Okay, enable high low is, do I show that? Yeah, enable high low, again, that's from MIPS. But enable high low is only used when there's a multiply in the execute, which there is not, so that would be a 0. Again, that's outdated, that's from MIPS. And reg select EX would be corresponding to the LUI. So when the LUI is executing, the reg select should be picking the upper immediate thing, right? Which is what? Input 1. You see that? It goes right here. Input 1. So that should be a 1. And technically I should say it's 1, but it's a 2-bit 1. Okay, then reg write EX for cycle 2 is going to be 1 because there's an ORI in execute. Reg write WB is going to match up to the LUI, which is also 1. Enable high low is going to be a 0 because we're not executing a multiply, and reg select EX is going to correspond to the ORI, which is just pretty much just going to be ALU, which is 2. So 2 2, D2. Next cycle, reg right EX is the multiply. So if this were MIPS, the reg right would have been 0 for a multiply, but because it's risk 5, the reg right's going to be a 1 for a multiply. Okay, because again, this has to do with the way that risk 5 handles multiplies as compared to MIPS. So this is one of the differences. But I'm going to put a 1 here because if this were risk 5, you do write to the register when you execute a multiply. Did you have a question?
I was gonna say, I think it's right, but I was gonna say the 2D1. That's not 2 bits of 1. That's 1 represented in 2 bits.
Right. So 0, 0, 1 in binary. That's right. Yeah. Likewise, this is 1, 0 in binary, and it's 2 because I have a D there, decimal. Okay, reg right WB is matching up to the OR I. That would be a 1 because the OR I is writing to a register. Enable high-low is, technically that would be 1 on MIPS, but let's just ignore that. And reg select EX is the reg select for a multiply, which is just going to be a 0. Sorry, not a 0, a 2. The defaults for this reg select, this is reg select, right? Yeah, the default for reg select is a 2 because most of the instructions are going to route the ALU through that mux. Most instructions write back to whatever the ALU produces, right? Now you might say, well, why didn't you make it a 0 then? I don't know. I think I literally made that decision when I was drawing this, right? You can design it however you want in your CPU, but I just used a 2 for this kind of ALU goes in the register, which is, I think it, like I said, I think it was just because of the placement of the ALU, put it down low. It's arbitrary. You can pick whatever codes you want. Okay. Okay, then the cycle 4, reg right EX, who's in EX? The MF high. That's a 0 technically. Again, it's MIPS, but in MIPS, the move from, oh no, I'm sorry, move from high does write to a register. Yeah, because you move a value, you move the high register into a general purpose register. Reg right WB, the multiply is in there. If this were, again, if this were MIPS, that would actually be 0, but because it's risk 5, I'm going to say 1. I'm going to say that the multiply does write a register. Enable high-low would be a 0, and reg select would be, who's in execute? Move from high. That would be whatever the reg select has to be for the move from high, which we don't even have marked on here, so let's not worry about it. I need to update the code for the new RISC-V, but you get the idea. Basically, the process here is you just look at whatever instruction is in the stage that corresponds to this control signal, and I've added suffixes to each of those control signals to signify the stage, right? And then it just comes down to understanding what the control signal does, and if you don't remember, you look at the design and understand what the instruction does, right? Whether it writes to the register and so forth. So you have to understand what the instructions are doing and what the digital logic components are doing. This is what ties together software and hardware, right? Okay, any questions about that? And of course, this one also includes the pipelining effect here too, that shows the instructions moving through the pipeline. So that's an additional dimension to this question. Oh, I forgot stuff. There's some additional stuff. Okay, that's cool. Well, reg select. Now, one of the things about this, by the way, is if you know what reg select EX is, then reg select WB is just a delayed form of that. So all I have to do to fill in this row for reg select WB is look at what reg select EX was in the previous column, right? Make sense? So I don't know what that one is. This one is just going to be go up and to the left, right? So that's a question mark. This one is up and to the left. That's 2D, 2 apostrophe D1. Up and to the left, 2 apostrophe D2. And up and to the left, 2 apostrophe D2. Oops. You see how I did that? So I just copied reg select WB is 1 cycle delayed of reg select EX, right? Because it's just a clocked version of the signal. So all I have to do is copy from here to here, right? Copy the value from the previous cycle. I don't even have to look at the instruction. ALU source EX is going to be, I don't have to look at the instruction, but that's pretty simple. So who's in execute in the first cycle? I don't know. And this one is LUI, so that's actually don't care because LUI doesn't use the ALU, so I don't care what it is. Then we have OR-I, so that's an I type, so that should be a 1, right? If it's an I type instruction, it's 1, R type 0. Next, multiply, 0, that's R type. And move from high is I don't care because move from high doesn't use the ALU. And then RDRT, which is also MIPS specific, and we don't have to worry about that. And by the way, this is something that the RISC-V does. This is one of the advantages of RISC-V. If you remember from 212, the RDRT was a MUX that determined what the destination register field was. Because in MIPS there were two destination fields, RD and RT. They're in two different spots, which is totally dumb. I don't know why they would design it that way. In RISC-V, they fixed that problem, and they made the destination register consistent across all the formats. There's only one destination field. And so as a result, we don't need this RDRT, and that's why you can create a fixed data path right here. The right address is a fixed data path. It's bits 11 down to 7. There's no MUX here to control that, right? So this is one of the things they fixed in RISC-V versus MIPS. Okay. All right, next question. What changes to the CPU design in question 1 would allow the CPU to execute the SLOV instruction? Okay, we can, this one is also something that's been fixed. So in MIPS, there was a shift left logical variable which took the shift amount from the register file. But in RISC-V, the regular shift instruction gets the shift amount from the register file. That's just the default, right? And you have to use a shift left logical immediate to get the shift amount from the instruction. You guys, I don't know if you remember that. It's kind of specific. But in MIPS, there was a special shift amount field in the R-type instruction. That's gone in RISC-V. They just use the immediate. They just use the immediate field for that now. Okay, so anyway, the question was, the question is, how would you implement that? Well, in our case, it's already implemented, but another question would be, how would you implement the immediate shift? Well, the way you're going to do that, and you're going to do this in your CPU, is the second input on the ALU is used for the shift amount, right? So you can get the shift amount either from the immediate, if you select ALU source to be 1, or from the register, if you use ALU source 0. You guys with me? So we used to, in the old version of this course, the ALU had a separate shift amount input. That's gone. We just use B now for the shift amount. And together, that together with this MUX actually gives you both versions of the shift, the variable shift and the constant shift. Okay, if you're confused by that, it's not a big deal. That's one of the MIPS RISC-V things. Okay, write a sequence of 2 RISC-V instructions that would trigger the register file bypass. What's the register file bypass? That is when you short circuit the register file, and instead of grabbing the read data from the RAM, you get the read data from the inputs, right? That's whenever you read and write at the same time. Well, what would cause that to happen? That happens whenever you have an instruction, like say an add. If you have an add that is immediately followed by another instruction that uses the output from the previous instruction as an input. So if you had something like this, a sequence like this would trigger it, because the first add would be in the write back stage, while the second add is in the execute stage, which also decodes, right, in our CPU. So the first add is going to be writing register 2. The second instruction is reading register 2, but the second instruction would normally get the old value of register 2, not the new value of register 2, unless you have the bypass. So the idea is that in this scenario, whatever I'm writing to register 2 should immediately get forwarded to the second instruction as the input, right? So we want to create a direct connection between these two instructions and bypass the RAM in the register file. You might say, why do you have to do that? Because it takes one cycle to write to the register file. We don't have a cycle because it has to happen immediately. We need a zero latency write in this case because we've got one instruction writing while the next one's reading at the same time. We don't have a cycle to write. We can't afford to take a cycle to write, and that's what the register file bypass does. So that would be a valid answer to that question. What would happen if the register file lacked write bypassing? Well, if that were the case, then you have to expect that instruction sequence, the second instruction would not be getting the new version of register X2. And if you needed to do something like this, and you needed the updated register 2, you'd have to put a no-op in between. You'd have to separate those two instructions with a no-op, right? So you'd have to basically stick a no-op in there, and then it would still work without the register bypass. So the register bypass allows you to avoid having to put a no-op between those dependent instructions. Now you could say, well, wait a minute, you don't have to put a no-op. Just take another instruction that you can find another instruction further down the program and move it into that slot. Yeah, that's called instruction scheduling. You can do scheduling sometimes. Sometimes you don't have an instruction to schedule in there, right? We're going to be looking at instruction scheduling in the graduate version, the graduate project in this course. Most of you won't have to do that, but I'll probably talk about it a little bit at the end, where you have to worry about rearranging instructions for stuff like that. Okay. Convert the behavior of the following Verilog module into a truth table. Okay, so this is a truth table. How many rows do we need? Well, it looks like there's 3 inputs and 2 outputs, so 2 to the third power is 8. So we're looking at an 8-row truth table. So we need, here let me say insert table. Come on, Word, what is going on? Insert table, we need 8. No, there's just one input, one output. Yeah, okay. So A and Y and I think we need one more row, right? Table. Okay, so A 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and so, okay, so Y, so this says if A2, so if the most significant bit of A is 1, which is pretty much just covers the last 4 rows of the table, right? Then the output is going to be 1, 1. So I can just put that in there like that. Okay? If that is not the case, but the second bit of A is set, which is these two guys, then the output is 0, 1. And finally, in the other 2 remaining cases, we're going to take Y and assign it to A, 1 down to 0, which is going to be 0, 0, and 0, 1. See that? Okay, so that's pretty easy. You just have to follow. You basically have to convert this high-level syntax into a truth table, right? I think that's a good question because that's what the synthesizer is essentially doing. The synthesizer is going to compile this code. It parses this code and essentially converts it into a truth table, right? That's what the compiler does. It obviously can be more complicated than that, but. Okay, write a system Verilog module named minority. It receives three 1-bit inputs A, B, and C. It produces a 1-bit output Y that's true if at least 2 of the inputs are false. Okay, so module minority input logic A, B, C, output logic Y, and module, and if at least 2 of the inputs are false, well, let's see. If at least 2 inputs are false, that would mean that, like for example, if I summed, the answer would be 1 or 0, right? That makes sense? So assign Y equals A plus B plus C equals 1 or 0. Does that make sense?
Can you go more in detail?
So so I want to assign the output to true if at least 2 of the inputs are false, which means that if at least 2 inputs are false, that means at most I can have 1 true bit. I can only have 1 of the inputs being true or 0 being true, right? So one way to solve that is to add all 3 together, and if one of them were true, then the sum would be 1. If none of them were true, then the sum would be 0, right? Right? You guys with me on this? Hopefully that's right. I think that's right. Now, by the way, notice that I'm converting this is one thing that you can do in Verilog. You can have a conditional expression and assign it to a bit, right? Yes?
So we're taking all 3 bits and converting them into a 1-bit value, and then...
No, 2-bit value, because I'm adding them all. So if you add, so I'm now, I think this should be fine. If you add 3 1-bit inputs, we want a 2-bit sum, right?
Yeah. So
another way to do that would be to use I mean, we could use a big if then else, obviously, right? But I'm trying to find a simple way, simple solution. I think
we don't want it to be 1-1 because that would mean that not 2 of them are false.
Yeah, if it was 1-1, if the sum is 1-1, then all 3 inputs are 1. If the sum were 2, then 2 of them are 1, right? In which case only 1 is false, right? We want at least 2 of the inputs being false. Yeah.
So the only possibility is 0.
Yep. Yeah, I think that's right. Okay, write a self-checking test bench for this module. Okay, so for that, you would have to say A equals 0. Actually, let's do it this way. Let's do A, comma, B, comma, C equals 3B 0, 0, 0, and then do a sign. Not a sign. We'll do a always. Always. Sorry, not always. Initial. Initial, begin. Test bench use initial, right? Initial, begin, set them, delay them, and then say if y doesn't equal, y should be true, right? In this case, y should be true. We expect it to be true because we have 3 falses and we just need at least 2 falses. So display error in input 0, 0, 0, right? And then we can just copy and paste this. 1, 2, 3. So there's 8 possibilities here. And then I have to, actually, you know, I bet I could add, I wonder if this would work. Can I just add 1 to this can I do this? I bet I can just do that. Yeah, I bet I can do that, and that way I don't have to change this. So I'll just say ABC equals ABC plus 1. So I'll do that 8 times, and I should get a counting sequence from 0 to 7. I've never tried to do that. I think it should be fine. Okay, then, and then I think you can even do this. You can say, I think you can say that, and then you can put A comma B comma C. There we go. Right? So that way I can just take this, and then I'll just, I'll just say, probably you could say 3B, 3 binary digits. Oh, and probably 0, 3B, so it'll put leading zeros, I guess. I don't know. And then A comma B comma C. I have to try it. Yeah. Yeah, so probably something like this, right? And then all I have to do now is check the output. So this is 0, this would be 1, this would be 2, this would be 3, in which case that should be a 0, 4 is a 1, 5 is a 0, 5 is 1, 0, 1, right? 6 is 1, 1, 0, that should be a 0, and 7 is going to be 1, 1, 1, 0. There we go. There's the test bench. Yes?
Can you go over when you use 2 symbols and 3 symbols when you're doing comparisons? Like, why wouldn't it be not equal equal as opposed to?
Oh, not equal equal is only when you expect to be able to compare the other 2 states, x and z, right? Technically, I probably, because test benches, I think you're supposed to use the you're right. I should have used bang equals equals, but I'm not actually using any x's or z's in here though. So in this case, it wouldn't matter.
Okay.
But like, yeah, that's for the test bench I taught when I lectured on it. I did compare to an x because there was a code I showed you where I had this array of test vectors, and the way the test bench knew it got to the end of the array was when it went off the last element, it would get an x. Does that make sense?
Yeah.
So I used it as a sigil for knowing when I got to the end of the test vector array. But in this case, I'm not doing anything fancy like that. So in this case, it wouldn't matter. But that's a great question. Yes?
Can you scroll up?
Oh, sure. Oh, I forgot the end, didn't I? Yeah. End. There you go. Sorry. What?
So it's that 0, 1. Shouldn't that third one be 0 if y times 0?
1, 2, 3. Yes. You're right. 3 is 0, 1, 1. Yep, you're right. That should be a 0. Yep. Yeah, 0, 1, 1 would have only 1 false. Okay, write a system Verilog module named majority. It receives 3 1-bit inputs x, y, z. It produces a 1-bit output A. That's true if at least 2 of the inputs are true. But the catch is that you're supposed to instance the minority module and use it to do this. So, so this one, I have to remember how we did this. So first of all, we need minority, minority, and we had A, B, C, Y, and I'm going to just have local signals here called A, B, C, and I'm going to just call it Y because the output of this module is called A, right? Yeah. So module majority, input logic ABC, outputs logic A. Is that what it says, A? Oh no, it's actually XYZ. Oh, sorry. XYZ are the inputs, and the output is A. So now I have to change this to XYZ, and here to change the actuals to X, Y, and Z. And this guy is going to be, I'm going to just call that Y. So I need to have logic Y inside here. And then the question is, if I know what the minority is, how then do I assign A? Is it just not y? So if y is going to be true if at least, yeah, y would be false if it was not the case that at least 2 of the inputs are 0. So we have 3 inputs, and if we know that less than 2 are 0, it would mean that 2 or more are 1, right? So all I have to do is instance my minority circuit, and I use the complement of the output of that, which I then pass to A, which is the overall output, right? So that's the answer. You guys see that? So this is just using structural structural Verilog. Okay, what's the purpose of the sensitivity list and the always statement? That's just whenever the state of any of the signals in the sensitivity list change, it activates the always block, or evaluates the always block, I should say. Blocking assignments, update the assigned values immediately. Non-blocking assignments, update the assigned values after all the actions associated with the current event have completed. How many clock cycles of delay will the code below impose on input to output, inval to output D? Okay, so this one is, it's going to take inval and assign that to A, and then A is going to go to B. The problem is that those 2 lines of code is just 1 cycle, because of the blocking and then non-blocking, right? And then these 2 are going to be 1 cycle. So the answer is 2 cycles, right? So even though there's 4 assignments, there's only 2 cycles of delay. Sorry, I'm going to going a little fast here. I want to try to get through these. Assume the CPU can execute the following instruction: add, subtract, BEQ, load word, store word. Which of these instruction has which of these instruction is the reg write signal not asserted? Does add write a register? Yes. Does sub write a register? Yes. Does BEQ write a register? No. So that would be one of them. Load word, does that write a register? Yes. Store word? No. So BEQ and store word are the 2 instructions where you don't write a register, and therefore the reg write signal never gets asserted when executing those instructions. Fill in the table for the module below. So this is another delay. This is actually pretty easy though. So A is the input, B is the output. So A is just delayed, right? So A0 is going to be delayed. So all I got to do is 0, 1, 0, 0. B delay is just the delay of B. B delay 2 is delayed of B delay 1. So 0, 1, 0. And B is the delay of that, 0, 1. So all I had to do here is each row of this table is a cycle. I have the input, so all I had to do is take this and shift it down, shift it down, shift it down, right? All I did was shift down because each of these is a delay of the cycle before. So whenever you have a delay, you take whatever was in the previous cycle and you move it to current cycle. Oh, it's just because of the, it's always underscore FF at pause edge clock. That's it. It's just, and I used non-blocking assignments in there. Sorry, yeah, non-blocking. I'm right. That's right. Okay. Okay. There's a few other questions I didn't get to, but I think they're just test benches. Another one. Describe any problems with the module below. This one is double driven. B is double driven because it's B is set. By the way, always at star is the same as always comb. It's just a syntax thing. But I've got 2 always statements. They're both driving the same output B, so that's not allowed. I think. Oh, and those always statements will create a latch. Because if you activate either one of those always and the if statement is false, the condition on the if statement is false, you don't tell it what to assign to B. So the synthesizer has no choice but to create a level-sensitive latch as opposed to an edge-sensitive register. And you don't want that. So you need to have a default output for combinational logic. That's important. Okay? So that's the other problem. Describe the process by which a user entered HDL is converted to a form that be loaded in the FPGA. Synthesis, synthesis and place and route, right? I didn't focus on that too much this semester. Describe the process by which an FPGA is programmed. You shift bits in serially, and that's it. Okay, any questions? I don't know if you guys noticed, if you program the FPGA, it takes like 20 seconds. That's because when you program an FPGA, it sends one bit in at a time in a giant shift register. It shifts them in at about a megahertz, or 5 megahertz, but there's a lot of bits that has to go in. Okay, thank you. If you have any questions about the exam, let me know. You have till Friday. Friday. You just have this week to take it.